Okay, welcome to Curve of the Earth measurement version 2. It's been 6 months since version 1 and we've come across a fair bit of data, so we've got a fair bit to get through, and it may take another video to get a result and come up with an absolute result. At the moment the data's coming in where roughly there's two points to flat and 3 points to round, so this experiment will show you where we've come to so far. I'm calling it an experiment now because it's a slight twist on the Wallace experiment of 1870, when Wallace discovered that he proved that the Earth had a curve in it. But you know that experiment is very controversial because the person who was his opponent at the time, Hamden, would not look into the telescope at the day of the experiment. He had some reason, and it may have had something to do with the optics. It was a 6-mile stretch, and also the mathematics. So the experiment that I've come up with is a slight twist on that, so hopefully we can clear up a few things. Our mathematics is a little bit new. It's a slight twist that my friends actually, I had really struggled with this mathematics, this 8-inch over 1 mile concept, and he explained it to me much clearer, and then it all of a sudden clicked and I could see where I was making my mistakes. So as a result, we've had to come up with more precise measurements with our water levels, and we had to increase our optics to get more magnification. So we'll go straight into the video now. The first thing we'll clear up is this mathematics. It seems to trick everyone, and I really had a problem with, so let's get into that. As you know, the standard concept is this: over 1 mile, if you draw a right angle tangent to the Earth, you'll get an 8-inch drop to the Earth. That's if it's round. Now, at this stage, I'm saying it's round only as a hypothetical. So let's move on to the next stage of this. The next stage of the concept is, let's move the tangent now so it pivots in the middle. So we have half a mile on either side, or 1,600 metres in total. Our drop will be 4 inches to the Earth, or 100 millimetres. So let's go to the next stage, okay, moving on with the concept. We still have our 1 mile distance and 1,600 metres. So I think we'll move away from imperial into SI units now. So let's start talking metric. I've introduced two columns into this concept, and they're 2 metres high off the ground. If we were to look along with our eye, we'll see the top of each column, but we won't be able to pick whether the Earth is curved or flat. Even though we put a column on a beam that can transverse the distance, if a hypothetical beam could go that far, we have no way of knowing if the Earth is curved or flat. Now, modern lasers are possible, will transverse this distance. So what we'll do is similar to what Wallace did in 1870. We'll introduce a centre reference of the same height. Now, this is a 2 metre column, and if the Earth is flat, we won't see this column rise. If it's curved, we'll see this column rise. Now, let's assume it rises and the Earth is curved, which we don't know for sure yet. So my friend stepped in to give me a hand with this now. I was really struggling because I had all this 8 inches and 4 inches and in my head. I couldn't quite comprehend it. So he said, "How high do you think that column is?" And I said, "Well, obviously it's 2 metres high because I've just placed a 2 metre column there." He said, "Now think negative logic here. don't think how high the column is, think how much has to be removed from the column to make it level with the rest. And this is how it all clicked when he said that to me. So I basically said, okay, well, I don't know. But his maths came up with a formula and removed 50 millimetres. So now my column is 1950 millimetres high. And that 50 millimetres is what we need to take off the centre column to make it level. And that 50 millimetres is the distance you have to your eye has to perceive to pick the horizon to determine whether the Earth is flat or round. Now, over 1600 metres, that's impossible. Your eye cannot determine a 50 millimetre distance over that distance. So when we look at the horizon, it'll always appear flat. Okay, let's move on now with our new mathematics of trying to chase this 50 millimetres over 1600 metres. Because of over the 6 month period between version 2, I did happen to research if there was a commercially available theodolite or some instrument that could measure a curve of the Earth, and I came up with the Leica TS16. It's a geostation made by a company called LEICA, Swiss company, probably state-of-the-art Swiss technology. Okay, can't be beaten. And they claim, according to this data sheet, that they can get an accuracy of in the order that we need over this period. In fact, they say that they can actually go to 3,000 metres. We're only after 1,600. I looked at the price of hiring one of these instruments, and it was out of my price range, and the cost is about $70,000. That gives you an idea what you'll be looking at. Plus the learning curve to understand how to learn it. It had to be trained on its use, so we had to go back to our standard where we were with the telescope. And of course we had to improve the optics and the cameras, and it just had to be a whole quantum leap in what we had to do to get the measurements needed and the accuracy. Because we're now chasing 50 millimetres. I'm thinking originally it was 200 millimetres, now it's 50 millimetres. So my friend came up with the concept that we'll still use Lake Tuggeranong, as I said, and the sandy beach end and the weir wall end. The only difference is we'll use the left hand side of the weir wall. Fortunately, Lake Tuggeranong has a boardwalk, and it's several precision made concrete columns with a chain lattice go around as a walkway, and they happen to be 1800 millimetres off the top of the water. So my friend said, okay, that will be our reference. Go to the sandy beach end and place another 1800 millimetre high pillar, and on the weir wall pick a smaller column, less than 1800 millimetres, and begin our measurements. If the Earth is flat, we will need to add 50 millimetres to our end column. If the Earth is concave, we will have to add remove 50 millimetres from our column, because the light will be coming in a curve up. If the Earth is convex, we will have to add 50 millimetres plus some extra. to compensate for the curve going the other way. So that's where we got to, and the next video you'll see will be the actual video and photograph evidence. Google Earth view of Lake Tuggeranong from the sandy beach via Piers 314 to the weir wall at 1530 metres. Aerial view of pier number 3. Aerial view of pier number 14. Aerial view of the weir wall, left hand side. Telescope and setup at Sandy Beach. Camera has been adjusted for perspective of human eye view. View to target now magnified 10 times. View to target now 20 times. Returning the next day with better lighting conditions and a telephoto lens to get a better view of the target. Times 50 magnification with Pier 3 becoming into view. Times 80 showing pier number 3. We've just reached the limit of the optics of the camera. We'll go to the bank on the other side to get a view of the peninsula showing the piers. View of peninsula showing pier number 3 and the buoy from version 1. View of pier number 3 and the weir wall coming into view on the left. Notice the reflected light on the bottom of the bridge. That will affect any light transmitted over the distance. Pier number 14 with the red marker and our destination, the weir wall. Once again at the natural eye perspective, see if you can pick that 50mm bulge or flat line of the earth. Telescope and variable slide mount using the sign at the sandy beach to achieve the rigid 1805mm precision level. Some beautiful black swans at the sandy beach. I just couldn't resist the photo. Laser level and 1 metre reference pole. 1 metre laser reference projected on sign at Sandy Beach. Measuring the height of pier number 3 at 1805mm. Measuring the height of pier number 14 at 1790mm. Measuring the height of the weir wall at 1695mm, which is 110mm short of our reference pier of 1805mm. The next clip will be the overall measurement using the telescope at the sandy beach all the way to the weir wall. You may also have to turn up the volume a bit as the microphone from the telescope is a little bit low.
I'm adjusting focus. Yes, I can just see the black strip. Strip is now 2mm higher. Doesn't look level. That's not level. That's level and just visible. So apparently we're within 1mm accuracy here. Yeah. seeing the light, of course. Within 1 millimeter accuracy on the horizon level. And 1 millimeter just above the what? The pillar, the bollard, whatever. Yep. And you think that's nice and vertical? Because I can't tell if it's leaning back or not. Okay, that's vertical. Okay, pack up, come back. Okay, do it.
Alright, we just might sum up now and go actually put the actual figures in. I've just added the actual figures in now. They're not very far off the hypothetical figures, as you can see. The main one we have is our centre reference pillar, which is still has just changed to 1805 millimetres off the water. Our sign at the telescope is now at 1805, matching the centre pillar. And the rear wall is in fact 1695 millimetres off the water, which is 110 millimetres short of these two heights here, which is excellent because it gives us this variation that we can go up and down with. The overall length from the telescope to the rear wall is 1530 metres, which is just 70 metres short of 1600 metres or 1 mile. The halfway point is 765 metres, so we didn't get the halfway point. The geography of the place didn't allow us that. But our main pillar, pillar number 3, is 1245 metres from the telescope. And we also have pillar number 14, which is directly in line with the line of sight to the wall. It is a bit lower than 1805. It comes in at 1790, and it would have come into play if the Earth had a concave curve to it. However, because it's quite a distance lower than 1805, it didn't really affect our figures. But I had it in there anyway, and it's actually 1310 metres from our telescope. So they're the actual figures, and what we'll do now is I'll just give you the results of our height adjustment. This is the piece of white polystyrene I was using at the rear wall to do all our measurements. This point here, the 1805, is the height of our reference pier, and this 1885 millimetre point is the point I had to raise the black line so my friend could actually see the tip of this black line just over the top of the pier, which was 160 millimetres above the weir wall. So this line here just represents this weir wall, so just imagine that's the weir wall. I think I've projected these points across over to the other line, almost line up with this drawing at the back. So the gap between what we should, if the Earth was flat, our measurements would have been in here. However, we had to raise our measurements to this point here with red line, and that actually ends up being 50 millimetres. So that's our figures that came in. Right, we'll just sum up now and just give you a brief going over what's next. So, what's next? Obviously, these results have still got a long way to go before we make an absolute proof that the Earth is whatever. Right now, it's looking like there may not be a concave curve to the Earth, just from the results we're getting from that pier number 14 and some other tests we've done. We're trying to, may have to improve our optics to another level. Our telescope's really at it's 200 magnification is right on the boundary of that telescope we have. Depending on how much money we can throw into this project. We already have an improved camera that we're experimenting at the moment. It's gone from, we're going to move from 1080 into 4K, give us a bit more quality. We really have to get some more experimentation into this light bending, because that'll be very controversial. People will be already picking up that, you know, this light bending will make some judgment. Also, we've got a fair bit of optics. There's a fair bit of research done on the camera and the telescope for long-range ground optics, which is there's a lot of research done on the web, on the internet and YouTube about cameras for viewing stars and outside the Earth, but not much on ground-based. So I've done a fair bit of research into this, and I think I'd like to pass this knowledge on, because there is a lot to know. Be able to put a telescope along and look along the ground where the air's thick, especially above water. There's also may put together the video of the follow-up from version 1 results. There was a whole lot of stuff came in there. Many months of research went into version 1, that follow on from version 1, and how light affected, how the atmosphere and waves reflected on the results. Absolutely incredible what came out of that. But that's where we sort of leave this for the moment. So thanks everyone for watching, and hope you enjoy this video.